Hello, everybody. Here we are starting our next unit, and that is a unit on solutions. And this is going to take me several lessons to cover the material. Today we will be going over an introduction / background to solutions. We will then proceed to answer these questions in subsequent lessons. For example, how can we determine which compounds are soluble in water? How does temperature impact the ability of water to dissolve substances? And how can we quantify how concentrated a solution is? And I've actually got 2 glasses here with tap water in them. Same amount of tap water. I've got some olive oil I'll place in here. Just a little bit. I don't want to waste my olive oil. A big fan. And then, of course, some sugar. There we go. Okay. And I'm making 1 solution, not 2. Only 1. And I can mix these all day long, but you'll get the idea here. It's actually kind of pretty, isn't it? That oil and water. Pretty cool. Doesn't truly mix together. This one, give it a little more time. You're going to have a complete dissolving of that sugar in the water. This sugar and water is a solution. Oil and water, however, is not a solution. Let's think way back to the old days. We're talking like September now. So as we start to think about solutions, I want to put that in context of some other things we've learned about way back in September. We learned about mixtures. And mixtures can be either heterogeneous or homogeneous. Well, my oil and water mixture here is clearly a heterogeneous mixture, whereas a homogeneous mixture is going to be consistent throughout. And homogeneous mixtures are solutions. Okay? So let me just go back here. This mixture, heterogeneous mixtures, like this oil and water, is clearly you can see that there's more than one substance in there. And because these happen to be 2 liquids, I have a new vocabulary word for you. They are said to be immiscible. Immiscible liquids are when you have 2 liquids that when mixed together do not stay mixed. And that's a good example here. On the other hand, we've got here a homogeneous mixture. You cannot see that there's any other substance in here. It looks like one substance. It's consistent throughout. And homogeneous mixtures are solutions. Now, just going a little up here to the side, the only way we can tell that we have a solution that is more than one substance in here, we would have to separate that homogeneous mixture. And we would separate it by a process known as distillation or chromatography. And you'll learn a little more about that in the near future. Okay, so let's go down here. So we're back here. We're talking about homogeneous mixtures or solutions. The solvent is always in greater quantity than the solute. So in this example, the solvent was tap water. The solute was the sugar. And this is important for you to be aware of, that water is considered to be the universal solvent. And that just means that water is all around us And it is so frequently the solvent, it's called the universal solvent. Could other substances be a solvent? Absolutely. But water is the most common solvent universally. Now let's look at some examples of solutions. I could take table salt and put that in water, and I get what? An aqueous solution. The minute you see AQ, meaning aqueous, we know we have a mixture, and it happens to be a solution or homogeneous mixture. This here is the chemical formula for sucrose, sugar. And this here is ethanol. And you could always use table R to be reminded what this substance would be. But we could place a liquid alcohol in water. We could place solid sugar in water. We can place solid salt in water and create solutions. Now, to add another vocabulary word here, because ethanol is a liquid and water is a liquid, we can say that they are miscible. When two liquids are capable of dissolving or dissolution, they are said to be miscible. Okay, so let's take a closer look at an example of making a solution, and that is using table salt, sodium chloride, in the solid form, and putting table salt into water in liquid form. The most common solutions are made with solid solutes and liquid solvents. If you recall from our past studies, sodium, a metal, chlorine, a nonmetal, makes an ionic compound. And if you look here, we have these partial charges. The oxygen end is slightly negative. The hydrogen ends are slightly positive in water. So these are covalently bonded atoms, and it's polar covalent. Okay? We need to think about that in terms of dissolving. And let me explain why. So, if I take this sodium chloride, you notice its lattice structure. Sodiums are the smaller ones, chlorine's the larger spheres. Okay, and there's like it's a formula unit. There's no end to it except the end of the crystal of salt. Okay, whereas water is a molecular compound. This is one molecule of water. When I place salt into water, we look here first. Sodium chloride solid placed in water becomes sodium ions, aqueous, and chlorine ions, aqueous. And I'm only showing the sodium ions here for simplicity. This process of an ionic compound dissociating or breaking apart into its ions is called dissociation. So we can visualize this with this particle diagram. You have the sodium ions, which are positively charged, and notice the negative end of those water molecules are attracted to that positive sodium ion. Likewise, the chlorine ions are negatively charged, and they're going to be attracted to the positive ends of that water. We can describe this in terms of IonDipole forces. For example, any ionic compound will dissolve in water, some more so than others, but ionic compounds by nature will dissociate into their ions when placed in water. And this leads us to a really important rule, and it's called the like dissolves like rule. Substances that are similar to each other in terms of polarity will dissolve in other substances that are similar to them. This is an ionic compound. It's so polar, it's ionic. These ions will dissolve in a dipole such as water. It's a polar molecule. So it's very nicely depicted here. This is an ion dipole force of attraction. And therefore, we can say that ionic compounds like sodium chloride or any polar compound will be soluble in a polar solvent, such as water. Like dissolves in like. Well, I just put sugar in water. Well, sugar is not an ionic compound. I mean, here's the chemical formula for sugar. By the way, pretty complicated. These are carbon rings making up this sugar molecule. C12, H22, O11. That is this one molecule. I placed solid sugar into water and it became aqueous sugar. Notice, I'm not breaking it down into ions. This is not an ionic compound. There are no metals associated with it. It is a molecular compound. So, ionic compounds will dissociate into ions and be attracted to water. But polar compounds, like sugar, will also dissolve in water, but they don't dissociate into ions. So you're just going to have these sugar molecules intact, all surrounded by water molecules. So like dissolves like is a polar compound in polar water. Like dissolves like is when you have ions in a polar molecule like water. On the other hand, what about this oil? An oil is a fat. This happens to be olive oil, so it's a plant-based fat. But any fat will not dissolve in water under normal conditions. Why? Think like dissolves like. Oil is neither polar and it's certainly not ionic. Oil, or oils, are non-polar compounds. And because water is polar and oils are non-polar, like dissolve like will not happen. So we can say here, though, non-polar compounds will be soluble in other non-polar compounds. So that's where the like dissolves like rule comes into place. Okay, so let's talk about colligative properties. When non-volatile solutes are added to water, the freezing point of water decreases and the boiling point of that water would increase. So it's freezing point depression and boiling point elevation. And we call these colligative properties because they depend on the number of dissolved particles as opposed to the type of solute. So let's just take a quick look using our examples of table sugar and table salt. Okay, when we put sugar in water, the solid dissolves in that water becoming an aqueous solution. If I were to put the mole concept in here, that means if I had 1 mole of sugar and I placed that in water, I'm still going to have 1 mole of sugar molecules in that water. But when I place an ionic compound in water, and let's say it's 1 mole of sodium chloride, because that sodium and chlorine dissociate, we get 1 mole of sodium ions and 1 mole of chlorine ions. 2 versus 1 unit. So let's apply this to the colligative properties. If I add salt to water, like I would on a wintry day, we salt our roads, because what this does is that salt, that solute, decreases the freezing point. Just a little bit, but enough to make the roads safer. We're less likely to form ice on the roads. And for every 1 mole of salt placed on the roads, we have 2 moles of ions produced that will interfere with the water and make it harder for the water to freeze. It'll actually depress the freezing point. So think about that. We have this sodium, it's kind of in the middle here. It's not allowing the water molecules to come closer together to freeze as easily. Well, guess what, folks? This may surprise you, but if I wanted to reduce icing in the road, I could put sugar down there. I could put sugar on the roads. Now, I'm not going to do that. Sugar is more expensive, number 1. And number 2, it's not as effective. Sugar will decrease the freezing point of that water. But for every 1 mole of sugar, you still have 1 mole of sugar molecules working to interfere with that freezing of water. Whereas you have 2 moles of ions that interfere with the freezing of water here. So the winner is, for financial reasons and for effectiveness reasons, salting roadways is much more effective at freezing point depression than putting sugar on the roadways. And suffice it to say, folks, when I add salt or sugar or any other non-volatile solute to water, it actually also elevates the boiling point just a little bit. That concludes our lesson for today. I hope you enjoyed it. Have a great day. Bye.